Okay, so hello everyone. Welcome to episode 62 of Warsaw Quantum Computing Group Meetups. My name is Pavel. I'm the organizer from the Quantum AI Foundation. And today we host our great speaker, K.Pomorski. He will give us a lecture about the strategy of integrated classical quantum chips development in Poland. Before we start, we'd like to thank our strategic partners for supporting us, Sonovero R&D, Onyx Alpha, Cogit, Quantum Z.io, and FinQubit. And we'd also like to thank our honorary partners. Yes, so that's all from my side for now, and I will now stop sharing my screen. And Krzysztof, if you are ready, the Zoom is yours. And first of all, thank you for accepting our invitation. Maybe just one more announcement before we start. So if anyone has any questions, you can raise your hand and we'll try to answer the question on the fly. But you can also post your question on the chat, and at the end there will be a Q&A session. Good. Krzysztof, welcome once again, and we can start.
All right, so welcome everybody. Thank you for this opportunity to give a talk. So I will try to be brief, and I will try to describe you some scheme of approach how to develop quantum chips in Poland using Polish infrastructure and having certain realism towards such huge task. So I'm functioning as a quantum hardware systems company, and also I'm working as assistant professor at Warsaw University of Life Sciences. And basically, I would like to share my experience since last 4 years, where I have developed certain types of quantum technologies. So basically, right now we have a board race in development of quantum technologies, and so far we have two dominant schemes or approaches. One is associated with superconducting electronics that has very low dissipation, and another scheme is associated with semiconductor quantum electronics that has better scalability than superconducting electronics, but has higher level of noise. And I would try to make usage of both types of electronics. So I would present with certain types of an approach how to tackle two types of structures and how to translate those things in quantum products. So basically, I will give very briefly introduction to quantum computation. I think there's a lot of people already very highly proficient in that topic. There's a lot of theory in Poland developed. Yesterday, it was a great seminar by Horodecki family, and Polish people are quite famous in quantum in description, quantum mathematics in a sense, I would say. But what is really missing in Poland right now is lack of this hardware, and the realism of technology usually comes from hardware more than just from theory. Nevertheless, two approaches supposed to be combined. So I will briefly describe you the architecture of superconducting qubits already existing, and then I will refer to classical quantum computer and IBM transpond qubits or Google transpond qubits, and then I will try to combine this with semiconductor quantum dots based quantum computation. So what is the classical computation? Well, it's quite simple in a sense. Formulation is that system has certain rigid logical states at the input, and via deterministic process, you have a certain states that results in this computation, which is usually a physical process, and usually, and this is a deterministic process. So you map certain zeros and ones at the input into 0 and 1s at the output. Usually, it's translated into continuous signals, as the word which is surrounded by us is usually analog signal word in a sense, but nevertheless we have very kind of deterministic and sharp logical states. So there's no much place for fuzzy logic at this stage. Nevertheless, later it can be translated into artificial neural networks, like classic artificial neural networks. From the point of view of theory, usually Newton mechanics gives you prescription how to build like mechanical quantum classical computer, let's say, and then you have Lagrangian mechanics, Hamiltonian mechanics, and you can also formulate everything by action principle, Hamiltonian by usage of Hamiltonian Jacobian mechanics. And that's kind of textbook issue in a sense. And there is a lot of manifestations of implementation of classical computers. Well, in World War II, there were some mechanical computers installed at battleships. So you can guide the guns to your enemy, and this computation process was incorporated in mechanics. Later, it was developed, translated into electronics, and then there was a big discovery of transistor, semiconductor transistor, by Barden and others. So there was a great development of microelectronics that is until today. So this is, in a sense, right now we deal with classical CMOS-based computers like our laptops. And those CMOS computers works in room temperature, and they're quite efficient, but still right now there is a lot of attention towards cryogenic CMOS-based technology. But this is still about implementation of classical computer working in lower temperatures, as for space applications or as assistance towards quantum computation. But if there is also quite famous implementation of superconducting classical computer by means of pushing magnetic flux. And this is rapid simple quantum flux electronics. This is by Likarev. That is Russian physicist that is currently living in the United States. So he was the father of these types of electronics just before the collapse of Soviet Union. And this is very low level consumption electronics. It consumes from 10,000 to 1 million less energy on one single logical operation. Okay, so this is so far, in a sense, very brief summary of classical computation. Of course, topic is much richer than just briefly described here. Well, when we deal with quantum mechanics, we, in a sense, we deal with so-called, I would say, stochastic determinism. We have certain quantum state encoded in inputs, and this is encoded, this is mapped to certain outputs, and there's obviously the superposition of two states and inputs. So that's constitutes a qubit inputs and qubits outputs. And usually the process takes place without dissipation. So we have Hamiltonian of a system which acts on a given quantum state and propagates and in a sense implements certain logical operations. I'm not going to deal with the theory. There's a lot of theoretical description of this phenomena. I will just today, let's say, focus on chip designs on chip schemes. There will be another talk that is focused on equations and on solutions. That today I just wanted to give experimental, in a sense, background. So this is like textbook issue, which I'm just describing right now. Well, this is more right now than 20 types of quantum technologies already existing. But if we analyze the prominent quantum technologies, we basically have 5 types of such quantum computers. Probably the most famous is IBM quantum computer, and known by IBM Quantum Experience, by this Qiskit usage that you can use. You can create quantum programs. You can run them on the cryogenic chips that are placed in dilution refrigerator at 10 millikelvin. So this is what you most commonly know. Of course, quite parallel to IBM activity, there is Google company activity. Their technologies are quite comparable. I'm not going to make any summary on their particular achievements because that's not the subject of my talk, but nevertheless, they're quite somehow similar. Apart from that, there is photonic quantum computers that emerged quite recently, starts to be also popular in Poland. Like they installed such computers at Polish Academy of Science in Warsaw, Center for Theoretical Physics, and Institute of Physics, Polish Academy of Science is going to buy such type of computer. There's right now neutral atoms quantum computers also present, and trap ions quantum computers. Trap ions have very long times of life of qubits, but they have problems with scalability. So in a sense, photonic quantum computers, neutral atoms quantum computers, and trap ions quantum computers, they all have a kind of problems with scalability. And that's why we should remember about quantum dots computers that are based on semiconductor quantum dots and single electron devices. They were initially implemented by Fujisawa and Peta, basically in 2003. And this was a dominant direction until it was taken by superconducting quantum computers. So you might wonder what's the real difference between them. Well, I would say superconducting quantum computers use the macroscopic wave function of superconductor. And this superconductor behaves in such a way that the ground state of superconductor is defending itself from external excitations. So that's why you have very low noise level in superconductors. And that's why it was chosen by IBM and Google, for example, and also IQM and other companies to follow. Well, if we nevertheless, superconductors allows you to have a medium integration ability. This is because of size of Cooper pair. So in superconductors, what is the foundation behind superconductivity phenomena? We usually use BCS type superconductors. This is about usage of superconductors like niobium, superconductivity in niobium. There is BCS theory that describes such superconductors. Those materials are quite simple by means of chemical compounds, and that's why they can be greatly scaled with nanostructures, with actually mesoscopic structures. The limitation size of BCS superconductors is basically due to superconducting coherence length, and this is pretty much the size of Cooper pair. So you have two electrons that are fermions, they pair into quasi-boson, so become a kind of boson. And then the boson-Einstein statistics applies. You have almost like first stage of Bose-Einstein condensate, and that's why this superconductor behaves as a kind of quasi-bosons. And so they have this particular feature that we are using. But the size of Cooper pair is not so small. So if we say in terms of nanotechnology, it's about 300 nanometers, let's say. You cannot go much beyond that, maybe 100. But if you go much beyond that, then your nanostructure is smaller than the size of Cooper pair, and your structure stops to superconduct. So you lose this superconducting property. So you cannot really downscale superconductors too much. So they can be medium sized. So the superconducting qubit is quite big. That's first disadvantage of usage of this technology. Second disadvantage, so already we can say that it already has shown certain level of saturation with its development. Like recent IBM quantum processor has like more than 400 qubits, almost 500. But let's say there's another feature that is very prominent for superconductors. It's actually about that you control this physical state by magnetic field or more exactly by vector potential. And so you need to have a source of this vector potentials, like a kind of solenoids. And the solenoids or waveguides, they take a lot of space usually. So that's another integration problem. When you try to go to million qubits or thousands qubits, it's really a challenging problem. So that's why a lot of people start to be aware that usage of superconducting technology has its, let's say, fundamental limitations, I would say. Um, well, let us talk a little bit on quantum dots. So in 2003, there was an experiment conducted by Fujisawa at Delft University and later in Japan and NTT, and quite parallel by Jason Peta in Princeton. And so they managed to control the flow of single electrons. And there was no, at that time, the structures was quite big. I would say almost comparable to the size of Josephson junction, but now they become smaller and smaller. And just to give you the feeling is that the transistors that you have in your laptop, I assume that your laptop is not too old, it's maybe at least 1-2 years old. Your laptop usually has the transistor with 10 nanometer of channel length. So the distance between source and drain in your transistor is 10 nanometers. So this is the level of technology already used on massive scale. So you can imagine that most recent models of transistor might have a 3 nanometers of channel length, let's say. So this is basically the size of quantum dots and the distance between quantum dots that you can have and then that you can use on a very massive scale. That's why there is a lot of coming back to technology basing on quantum dots, semiconductor quantum dots, and a single electron-like quantum dots in a sense. But not only that, also spin-based quantum dots. So it's quite necessary to retrial this approach to single electron devices as possible implementation of possible implementation of quantum computer. And then we have quite spectacular achievements of Dirac company from Australia. You can trace their work. So they start to build more and more reliable qubits in semiconductors. Of course, the performance is still much beyond superconducting qubits, but still they have, in a sense, much better potential of growth. So what I try to say, I don't try to compete with superconducting technology or with a semiconductor technology, because I'm quite sure that there will be emergence of two types of quantum computers in the next 5-10 years. And both will be a kind of operational. What I try to do is I try to combine them into one new, into a new type of architecture that can make use of both advantages and try to compensate disadvantages of those two types of technologies. All right. So this is, let's say, let us briefly study or review rather the work on Josephson junction physics. So there's supposed to be mentioned what is a Josephson junction. I mean, that's not so much common knowledge, since usually we have a common knowledge about transistors. So Josephson junction is the object that has, you have superconductor, insulator, superconductor. You have such structure that has high nonlinear IV characteristic, current voltage characteristic. And superconductors allows you to have a current flow with no dissipation. And basically using a kind of transistor that's not exactly equivalent, Josephson junction, it's not exactly equivalent of transistor, but is somehow comparable from functional point of view. You can code basic 4 or 5 types of basic qubits, let's say 3 types at the beginning, which I'm going to mention. So the Josephson junction is denoted by X sign. So you can control Josephson junction by voltage. So you have superconductors, insulators, small superconducting island, and you have voltage gate that you can control the presence of Cooper-Person small island. So you have so-called Cooper pair box. So that's a option. Then second way is to have superconducting nanowire. It's closed. It's it's in a sense interrupted in one place by insulator. So it's a flux-based superconductor. That's option B, phase, so-called phase superconductor. That magnetic flux, that's a B. You can have its variation with free Josephson junctions. So again, the same nanowire that is closed and there's interrupted by free insulators that create free Josephson junctions, free X's, as you can see. The system is biased by external solenoid. So this is what happens here is that magnetic field enters the loop and then it's quantized in Josephson junction. It's quantized, so you control this state of the washboard potential, which you can see on the right, by either voltage, which is the uppercase, and the magnetic flux. There's also the option that uses so-called phase. Well, so you send the current via certain value of current via Josephson junction, and then you control the occupancy, the shape, in a sense, the shape of this washboard potential, and there are certain energy levels which can be exploited. So in your quantum computation, usually you exploit ground state and excited state, and since you want to be as close as possible to the ground state, it's stable. This is known from quantum mechanics that ground state cannot basically decay. So that's why you are using dilution refrigerators. So all these devices, which are described here, they are using dilution refrigerator. That is a mixture of helium-3 and 4. That's quite costly equipment. Still, we have quite few pieces in Poland, like Institute of Physics. Polish Academy of Science has a dilution refrigerator with the Professor Zgir's group and Professor Dietl group. There is dilution refrigerator, I'm sure, at University of Warsaw. There is a dilution refrigerator at AGH, University of Science and Technology in Krakow. There is a dilution refrigerator at Institute of Low Temperature Physics and Fundamental Research in Wrocław, in Polish Academy of Science, and so on. So we have like 5, 10, such, at least in Poland, such devices that are kind of operational that can be used for quantum experiments. All right, so that's just brief introduction to this superconducting qubits. And then, okay, well, I have not mentioned yet the most commonly used architecture. That's a combination of let's say, option A and B, essentially. So you have the squid loop that is controlled. So like, squid loop means two Josephson junctions in parallel that is controlled by voltage and magnetic flux by both of them. So this system has quite low level of noise. So here there's mixture of control by electric and magnetic fields in a sense. All right, and so this is again these types of superconducting qubits, and you see various companies using it. Right now, it's really common. I mean, basically, every big industrial group has already a kind of qubits associated with superconductors like IBM, Google. In Europe, you have quite recent usage of IQM, Rigetti, and so on, so on. So there's a bunch of companies, like in Poland, quite recently. It's IQM that is quite active. Yeah, and there you have very massive, in a sense, approach from D-Wave company as well. So yeah. I'm not going to describe this in greater detail because there's a lot of progress and there's a lot of work. So that's just a brief introduction. Okay, so let me move to single electron devices and Fujisawa work. So basically, that's a system that was studied by him. So he essentially by using voltage biased gates, metallical gates, he creates effective potential that generates certain minima, and in this minima, your electron can live. So this is left and right. So effectively, two quantum dots are generated, and then but basically then one electron wave packet is between left and right. So it does oscillate, does tunnel. So this is Fujisawa work. Okay, so quite recently, there is a work from MIT that tries to use both type of, let's say, schemes. So tries to link two types of technologies. So you have transmit qubit that's in superconducting qubit that is, in a sense, in the center. And on the left, you have a semiconductor quantum dots. So actually, this is work from 2024, and I have quite similar scheme from 2019 and 2020, which I will refer later. So this is just to underline the importance of this direction, why this direction is supposed to be prominent. And so basically, yeah, I mean, yeah, I will give more and more description on similar hybrid approach. So this is hybrid quantum system approach that is used. Okay, quite recently also there is a work by Gawelczyk from Poland. He's quite much associated with United States as well. So he's from University of Wrocław and from Toruń. And what he does is he builds the arrays of quantum dots. That's his work. From this year, he has a lot of work on that subject. He's excellent collaborators, also with United States. So basically what he does, he builds array of semiconductor quantum dots. And then you have source and drain. So in a sense, and then there's polarizing gates, G1 and G2. And then you can see the flowing current. So that does depend on its contour plots that are given here. So it has definitely the features of, so it depends. You have in picoamperes, it's quite small numbers. So this is quite excellent work, which is by Dr. Gawelczyk, which is also aligned with this let's say with this proposal, which was from 2019 and 2020 and from 2024 work of MIT and so on. So so this scheme has a potential to be expanded both in theoretical perspective and into hybrid form as well. Right, so let me move on. Okay, so let me briefly concentrate on the structures and on the philosophy of single electron devices and so-called position-based qubit. This is much less. So this is, in a sense, I'm coming back to work from 2003 and 4 because of recent advancement in nanotechnologies and in lithography techniques that allows you to build very repetitive structures. So we have quite big potential in Poland in this direction. There is Institute of Microelectronics and Photonics, Łukasiewicz Network in Warsaw. We have CESAMAT associated with Warsaw University of Technology. And also there are other centers that also can do better and better lithography. So I just wanted to give you a brief scheme how things can be understood. So most schemes were well known. Let's say 95% of quantum technologies, what they do, they encode information by usage of eigenenergy states. So you have a quantum system that has discrete quantized energy states, like spin qubit, for example. So you encode it by superposition of those two states. So this is the most common technique. But here, how you call the scheme of encoding of quantum information is different. What you do is you are using so your presence of electron on the left quantum dot is associated to logical 0, and the presence of electron on the right quantum dot is associated with logical 1. So this why it's position-based qubit. The scheme of translation of this quantum information from position-based qubit to energy-based qubit is quite straightforward. I will give you some link to my work on that subject, but that's already well-known scheme. So let's say the way this is more compact way of doing. So in a sense, the position-based qubit allows you to have a better, in a sense, more compact density of quantum information. That's what I try to say. Of course, there is a price to be paid for that, and this is the coherence and so on. Nevertheless, in theory, it gives you better density of logical states in a sense. So your basically electron basically moves back and forth. There are two minima in effective potential, and those minima can be interpreted as quantum dots. So usually there is a lot of attempt right now from Silicon Valley and also from big players like, let's say, like Recon, like Jülich in Germany, and also a lot of people from Silicon Valley try to functionalize the existing transistor to be represented effectively as a system of two coupled quantum dots. So you have source and drain that can be the functionality assigned to left and right quantum dot. And then there is a voltage gate or voltage gates that control effective potential. If you are using two such single electron lines, like what you basically have is Coulomb repulsion between two electrons, and then having Coulomb repulsion, you have like anti-correlation of electron positions. So in such a way, you can build a philosophy of designing the quantum gates. So basically, you can just imagine you're trying to design the logical gate using charge balls. Just try to think classically, charge balls. You're using this repulsion principle. So what is described on the right side is actually the inverter, logical inverter. So what I would say is this: if your electron is, let's say, here on one side, on another side it will tend to be here. So it's like negation of, so this is like logical 0 is negated into logical 1 and reversely. So this is like kind of swap gate in a sense. So you can generalize this way of thinking to CNOT gates and so on and so on. So you arbitrarily build any type of quantum gate. Of course, in quantum regime, it's more kind of blurry picture, but still the philosophy is quite, is like taken almost from classical work at some point. Okay, so that's basically the philosophy. Then let us briefly review what happens in Josephson junction. Basically, it's nonlinear harmonic oscillator, what we can say. So, so basically, many people would say to you that Josephson junction is extremely expensive nonlinear oscillator, and harmonic oscillator. Of course, if amplitude of oscillation is not too big, it can be linearized. So you have two possible regimes that are described here. And then you have a transband qubit on the right side that is dealing with this nonlinearity. You have cosine, and then there is Cooper pair box, and then you have linearity. So basically, it's linear oscillator at some point. Of course, this unharmonicity gives you certain correction to energy levels, but still, this is basically this concept. So your basically superconductor is ideal inductance, as you can see. And since the superconductor is interrupted by insulator, that's why you have the capacitance. That's it. Okay, and then you have the philosophy of quantization of energy levels in harmonic oscillator with neglectance of unharmonic term or without neglectance. But you can do it. It's quite straightforward procedure. Okay, so let me move to more kind of advanced concept. So basically, what happens if we have a Josephson junction system, like superconductor, insulator, superconductor? Just forget about this black. It's you can make it voltage, but apply voltage, but still. So what you have in Josephson junction is underbound state. Essentially, it's underbound state. So there is, in a sense, electron. So in this between two superconductors, you have lower level of energy levels in a sense, and then there's movement of electron is reflected as a whole and so on and back, and this whole is reflected as electron. So this is Andrew-bound state, so-called, since you have Andrew reflection. And in this Andrew-bound state, it basically describes the properties of Joseph's rejection. And what is proposed here is this disturbance to this Andrew-bound state. So this or deformation of this Andrew-bound state. And this is done by system of two semiconductor quantum dots where you have movement of electron. Of course, you can amplify this effect quite much because remember, the size of superconductor is quite big as in relation to the size of quantum dots. So you can have 10, 15, 20, 100 quantum dots alongside of Josephson junction. So you can amplify this effect. So what you can achieve here is that by this interaction of these two quantum systems, you will get extra system that has extra properties. And since there is paradigm of control of Josephson junction by solenoid or by other sources of magnetic field, that you are usually, they take size. So you can change this paradigm by using of this quantum semiconductor quantum dots. So they are controlled by voltage bias, and these metallic cables can be quite small size, like 2 nanometers of diameter or smaller even. So that's why this is a very compact scheme of controlling Josephson junction that goes beyond commonly used paradigm. So I would say whenever you try it, I will later give you a kind of scheme how to think about quantum neural networks from the perspective of quantum dots, but still there is a lot of technicality, and this is kind of encoded here. So moving electron in between left and right quantum dot generates time-dependent electric and magnetic field, and this magnetic field is imprinted on the state of Josephson junction, so you can see the IV characteristic. Yeah, and so that's basically the principle. So this interface, which is described here, is so-called electrostatic interface between quantum dots, semiconductor quantum dots, and Josephson junction, superconducting Josephson junction. But you can, so basically this interface is described here on this picture. So you have semiconductor nanowire, the violet. There are some voltage gates on the top that bias, that generate effective potential. There's moving electron. And in nearby, you have Cooper pair box, so superconductor, insulator, superconductor, Josephson junction that is biased by some electric field. So you have this electrostatic interface present here. That's one possibility. Another possibility is to have it, in a sense, D-wave company way of thinking. So what you have a flux, so closed loop, superconducting loop interrupted by Josephson junction. So you have flux, the qubit, which I described at the very beginning by Franco Nori work and from 2005 and before. So you have, in a sense, superconducting qubits interacting with closed semiconductor nanowire, where you have the electron or electrons. So then you have this interaction by inductance by magnetic field that potentially generates you less noise. But that's a kind of presumption. So this work is kind of described here. So it's just brief concept of this interface. Then there is also this concept of quantum neural networks. I just, let's say, just proposed it like 2008, but this is 2018, but this idea is somehow probably even older. So what I'm saying is that imagine you have a chain of quantum dots, semiconductor quantum dots, that are kind of coupled, so the electron can tunnel from one red quantum dot to another red quantum dots. And then you have metallic gates in between that controls you this connectivity between quantum dots. So what I'm saying is you can inject certain electrons, and then you can propagate them, and then such system can mimic you the quantum neural network that is somehow mapped to the problem of quantum transport. So you can think how to train such quantum neural and so on. So that's one of the schemes with possible implementation of quantum neural network at most kind of fundamental level. I'm not saying this is the best of best, but that's one of the possibilities. Okay, so right now we have commonly used so-called transmon superconducting qubits. So you have two Josephson junctions in parallel, basically it's squid. So you have two small superconducting island that is coupled to some metallic gate from one side, and then you have bigger superconductor. Anyway, this is commonly used technology that is already mastered by many sites, many countries, and so on. You can find also a lot of open source code describing it as well. Well, unfortunately, this technology is not present in Poland, at least to my knowledge. Nevertheless, I believe we have the potential to do it. There's MACTOP project in Polish Academy of Science, in Warsaw Institute of Physics, and also besides that, I would say, let's say it's hard to say who is the best person to pursue such direction, but let's say I would say Professor Zgierski is not far away. Nevertheless, he has slightly different activities right now. Nevertheless, he has a big potential of creation of Josephson junctions on and also experiencing that. Anyway, that's a possibility. So it's somehow necessary to think seriously about quantum technologies in Poland by constructing our own qubits. It's a lengthy process that can be speed up by people having expertise. Nevertheless, it's absolutely doable from a lithographical perspective because the lithography, I would say, resolution down to 50 nanometers is absolutely fine. I would say even resolution down to 100 nanometers is satisfactory for this type of technology. So we have already existing lithography, and there's certain existence of dilution refrigerators. So we have all ingredients from, the experimental equipment to do it, but we don't do it. That's how it is. All right. So there are various zoo of this transmon qubits, superconducting qubits. I'm not going to discuss. I'm just going to briefly give you a scheme of that. And if you talk about materials, it's not the titles that misleading still refers to the previous slide, but let's say it will also be associated later with that. So if you talk about materials that are used by IBM, this most recent processor. There are materials used, NBN, aluminum oxides, such materials are used. So they are absolutely accessible and can be mastered. The usage can be mastered by Polish institutes as well and the European Union institutes as well. So just to let you that how this is done. Okay, so let me now move to a reference of existing technologies in Poland. So there is certain work of Professor Guziewicz and Dr. Swish. He unfortunately, Swish passed away, but Professor Guziewicz also has this expertise in creation of superconducting single photon detector. So I've just mentioned that this technology was active in 2011. There was a certain project accomplished. Of course, you need to talk to Professor Guziewicz on details, but there is certain work by him that is published. So this project was done in collaboration with Professor Sobolewski from Rochester University. So basically, Poland has this ability of detecting the single photons hitting superconductor. So I would just briefly mention the principle. So you have superconducting, in a sense, layer that is quite thin, that is close to transition temperature, that is close to transition from superconducting to non-superconducting. So it's like transition-based edge detector. And there is a photon hitting in superconductor. And this photon deposits photon, like quanta of electromagnetic radiation, in a sense, or photon from optic fiber, deposits its energy. And what happens is that there's hotspot that appears in superconductor. This hotspot is not superconducting anymore. So and you are biasing the superconductor by certain quite static big electric big electric current that is non-dissipative. When this photon hits, it generates dissipative center. So you see this its presence on IV characteristic. So there is sudden spike in IV characteristic, but this spike has a tendency to decay quite quickly. So this, in a sense, dead time of this detector is quite small, as in comparison with semiconductor kind of analogons of that. So this is already working, but this can be extended, or this project can be reactivated. It's not yet, it's already finished, but it can be reactivated. And there is certain expertise in Poland that can be used to create like array of such device, like camera of such detectors. So you can use this in astronomy, in telecommunication, and many other, also in quantum technologies. So this is, in a sense, I would say, I would characterize this presence of such devices as light level of quantum technologies, because definitely system here shows the quantumness, but of course there are various ways of categorization of quantumness. That's how it is. Okay, so that's just one positive news. So this is a good starting point if you try to think about existence of technologies. So you have Professor Guziewicz, and you have also Professor Zgierski. In a sense, almost these very two buildings that are very close to each other. So that there is a potential. Okay, now let me describe some principles of rapid single quantum flux electronics, as this is the way to make approach to quantum computer in superconductor more realistic. So there's a lot of entities worldwide that already are able to manufacture transmit qubits, a system of 10, 15 qubits, interacting qubits. But this is very small quantum computer or small quantum chip, and it's not fully justified to use 10 kilowatts of dilution refrigerator to make such small number of qubits fully beneficial from business perspective. So what is more realistic, and in my view, it's supposed to be pursued by European Union and also by us, is to use massive superconducting classical computer that's using the scheme of rapid single quantum flux electronics, which I will describe in quite detail right now. And this will be later coupled to big massive circuit, superconducting circuit that is coupled to smaller smaller quantum superconducting circuit. This is more expensive. And in such approach of having hybrid classical quantum computer, it's much more feasible from business perspective, and in a sense also realistic from technological perspective. So what is the principle of operation of rapid single quantum flux electronics? So let's say there is a first phenomena that is important for superconductors, is existence of vortex. What is a vortex? Vortex was discovered by Abrikosov, and he was awarded Nobel Prize for that. Unfortunately, Abrikosov already passed away, but it's, so you have superconductor, and this superconductor can be locally punched by a magnetic field. And in this, when you are moving on the closed loop, after closed loop, you need to come back with the phase of coherent wave function. That's why you have the quantization principle. So in a superconducting ring, you have quantized magnetic flux. So imagine that you have some region of less strong superconductivity on that side, and you apply some voltage to weaken the superconductor even more. Just be aware that voltages, superconductors doesn't like voltages. So you're supposed not to go, basically be in the range of nanovolts or at most millivolt, but much below 1 millivolt, because you can kill superconductivity easily. So you can weaken superconductor locally by applying certain voltage, and then this magnetic flux can have tendency to be pushed, to go away from this loop. So in that way, you can push by weakening locally superconductivity by means of current or sometimes voltage, both. You can transport magnetic flux. Actually, it happens that you can transport with very low energy cost, and that's why this technology will be so attractive. So that's how it is. So you can push it out, and then if you have Josephson transmission line, so you have superconductor Josephson junction, superconductor Josephson junction, so on, you can transport this. And then the one quantized magnetic flux in presence of one loop, as given here. So it's a chain of squids in a way. Have a chain of squids, superconducting squids. So you are transporting the fluxon, quantized magnetic flux. And then the presence of magnetic flux in one squid means logical one, classical logical one, and lack of its presence is zero. And this is the principle of rapid single quantum flux electronics. I'm not going to go into detail, it's just brief introduction, like there is model, let's say two-fluid model that can account for that. Okay, and then you can apply, basically people read there was a Yoshikawa at the Hypercomplex Seminar 2024 in Łódź, and yeah, um, and then he's quite excellent in designing the microprocessors, superconducting microprocessors that can run with a clock of even 100 gigahertz, but they consume from 10,000 to 1 million less energy on one operation. So we are at this stage of technology development where, on the level of mainframe classical computer superconducting processors can replace semiconductors due to energy usage. That's how it is. So that's already existing technology. There's some problems with random access memory, but still, this technology does exist. And so this is just example of classical gate, how it can be implemented in Josephson junctions. Obviously, I don't have much time to go into details, but this is absolutely scalable process and well understood and so on. So there are different schemes of implementation of the rapid signal quantum flux electronics. There are four, in a sense, four different types of schemes. In a sense, competitive, but I would not even say they are fully competitive because each of them has certain advantage. Somehow the less very low level usage is adiabatic quantum flux parameter by Yoshikawa from Yoshikawa National University. And this is the scheme, I'm sorry, described here, but I'm not going to describe this in detail. It's just to let you know the circuit scheme, how it can be. There is Nagoya. Actually, I was at postdoc with Fujimaki. So this is Josephson junction, also low voltage single flux quantum. So this is used at Nagoya. And there is a Hypers company in the United States, Mukhanov, right now probably he moved to another company, but also associated with this type of technology. So there is different scheme, and also North Group, Grundmann is using slightly different scheme. Mukhanov is postdoc, was PhD of Likarev, the inventor, and so on. All right, so that's the technology that is associated with rapid single quantum flux electronics, or kind of this type of electronics that implements superconducting classical computer. Then you can even talk between two types of technologies from previous slide. Adiabatic quantum flux parametron can be interfaced to a single flux quantum. And then, so you need to understand that this guy is very low noisy, so it can operate at 10 Kelvin, and this guy usually operates at 4 Kelvin. So when you try to interface two types of systems, like a classical superconducting computer and superconducting qubit, you need to think about these interfaces. All right. So that's just briefly the scheme that does exist. There's a work associated with that and so on. I would say from the point of view of functionalization of superconducting electronics, this perspective of having massive classical superconducting chip interface to qubit is actually this one, and this is the interface how to read the state of qubit using rapid signal quantum flux electronics. Obviously, there's a lot of work already on that topic, so this is possible. So in a sense, this slide from certain perspective is the prescription how to even go into very fancy concept of classical quantum mining, because I will later show you the possibility of implementation of neural networks with Josephson junctions. So we can have classical neural networks somehow run by rapid single quantum flux electronics that can talk to local quantum chip. So you can try to build a kind of mind, artificial mind, classical quantum mind in superconductor. Okay, so let us be a little bit more realistic, coming back to Polish, in a sense, perspective and environment. So there's already work on integration of superconducting single photon detector with rapid single quantum flux electronics. That's one of the work. So I would say this is absolutely within somehow Polish possibility, in a sense that we have certain friendly contacts with certain sites, so we can exploit them. So we can try to make this technology to come back to Poland and be reactivated. So this is for the purpose of astronomy. Even let's say you try to build very sensitive camera in your satellite that try to detect very weak sources of light, you can use this scheme as given here, even for astronomy purposes. So, and then obviously, if you have a superconducting single photon detector, it's a superconducting electronics. It's better if superconducting electronics is driven by superconducting electronics, not by semiconductor electronics, because this interface is quite terrible there. All right, so then there's a prescription how to create a Josephson junction neuron. I'm not going to give you details. There's some work already on that existing. This is already a running work by many sites. Basically, you have such scheme of Josephson junctions. So remember, this is inductance is superconductor Josephson junction, and yeah. So the system is equivalent to two coupled differential equations, ordinary nonlinear differential equations, and this generates use characteristic spikes are for spiking neural networks. So I just refer you to some work on that. So just mention that does exist. Okay, and then if you say about the sizes of every single quantum flux electronics, I'm saying like Josephson transmission line and so on. So this is not so small. It doesn't have to be that small. This is already a chip, so absolutely doable in many labs in Poland, I would say. So it's just a question of political will and technological will to go for that. That's what I'm trying to say. Okay, so let us move a little bit more into kind of political background, maybe not political institutional background, but of course also is this bias, some kind of scientific policy as well. So let us review the possibilities. I don't want to say there might be more existing centers. I'm not fully aware of them, but let's say I tried, this is my personal view or kind of insight. If I try to search for potential that can be activated, that's my kind of personal perspective. So far, I would say because of this superconducting single photon detection, Institute of Microelectronics and Photonics in Warsaw with Łasiewicz network represents very big potential in their activation. There is a CESAMAT that has a lot of lab spaces, but I would say they are quite new, and let's say that I would rather start from the Institute of Microelectronics and Photonics. Nevertheless, they might be also possibly interested. Then definitely have a Polish Academy of Science Institute of Physics in Warsaw, and there's Maktub Group, and very particular is Zgierski, Professor Zgierski is very, he already showed to me some time ago at least 15 Josephson junctions on one chip. Somehow he's not going, he didn't went to full scale, but he has certain potential and temperament to do it. Then there is definitely Institute of Low Temperature Physics in Wrocław that has certain experience in microorganic techniques. Maybe not so much right now oriented on Josephson junction, but definitely they have excellent dilution refrigerators. They have already constructed them. So this is the excellent place for possible samples characterization if the capacity of Professor Zgierski and others is not is overloaded, then we can do it in Wrocław for sure, under certain agreement or prospective agreement. Then there is definitely adjacent University of Science and Technology that has its own dilution refrigerator, Oxford dilution refrigerator, and there is ATSMIN, so-called. And then there is University of Warsaw, Jagiellonian University, but I don't have that deep knowledge about the current status of apparatus. Probably they have slightly different priorities than just going for Josephson junction physics, as I would say. All right, I have not mentioned Wrocław and Nicolas Copernicus Institute in Torun by the matrix array, which I have already spotted, but I don't have full knowledge on that, so I'm not going to touch this topic because I know that this what I'm saying is about this array. So I'm fully aware that of samples of that work are by NIST in the United States, but a very good institute. So so definitely they have, even these experimental results show excellent access to facilities, but most likely associated with the United States. All right, so that's how it is. And okay, so that's a brief characterization of political organization structures. All right, I'm going to finish quite soon. Yeah, I'm sorry for this kind of yeah. So let's say yeah. So let me briefly describe you what's the philosophy that drives me or are supposed to be maintained, and then I want to say something which is a little bit of drastic nature in a sense, that Poland is a place of science development and fundamental way of thinking, but is a little bit behind technology. And this is partly associated with certain mentality and temperament of people that live in academia. So right now, usually the scientific worker is evaluated by ministry points and publications associated with ministry points, and nobody really takes into consideration hardware as priority and operational software that might emerge. They usually just think about publications on any subject. So this already hits in, I would say, in the priorities. Second thing is most scientists in Poland prioritize publications, not patents. And this is, if you want to develop technologies, you have to prioritize patents first. And publications are just additional, fruits that goes with that. Then next thing is prioritizing experiments, implementation and execution, and technological process development over theory development. So Poland is full of theory. It's like, but it's not really. It's of course experiments are more costly, but it's always kind of behind in technology perspective, and that's not just due to financial reasons, but it's due to mentality that is maintained. That somehow the theory is always worshipped as the first thing that's supposed to be. That's not necessarily true in the real technology development, in the real technology pursuit. Then another aspect is habits. So we usually try to put all details in the publication that we want to, all details we know. And this is wrong if you are acting in competitive environment of certain entities that has also some commercial interest. You cannot put all details in the publications, so try to release on a certain part of your know-how and the rest keep it for yourself. Then another thing is thinking in terms of quantum products as the first priority if you want to go for quantum technology. So you want to be competitive. So you need to think about new type of quantum game or new type of qubit architecture and so on and so on. You cannot think about always think of science first. No, technology first, and science just always accompanies with that, with novelty in technology. That's quite obvious, and this is what is shown by Google, IBM experience. They drive science by technology, competitiveness. And there's the last thing, which is also very crucial, which starts to be more prominent year by year, is the need for pre-training your own students and staff. You are, I don't know how much money you need to have to employ somebody from outside, but don't believe in miracles. And people will not come from just like that. And you have to rely on some local potential, and you have to develop this potential, especially under the circumstances of education level that is going to less and less, and also motivation level. The young generation has much less motivation than the old generation, so on and so on, due to the times of consumptionism and so on. But nevertheless, that's a real issue. So you have to keep in mind this update of academic values if you want to be on that path. That's a kind of, at least, remark from my personal point of view. Okay, I would just very briefly describe what I'm doing already in reference to what I have described. So I have certain products that I'm right now developing. The quantum interface, software, hardware, that's new designs. This is what I do. Especially that there is MIT presence. That shows me also the prominence of the topic, which was chosen for much before. Then there is a quantum chemistry hardware solver, which I already have under development, especially in the modeling case. And I'm now under the stage of saving the intellectual property associated with that. I'm not going to put many details on this particular product, but I'm just signalizing I do have team and potential and pursue and activity in this direction. Another product where I'm going to develop is quantum neural networks. That's tough stuff, but still, I believe this needs to be exploited, probably under slightly more generalized circumstances already described. And then my last products are quantum emulators of classical emulators of quantum computers. Basically, classical RLC circuits can model the quantum system. I would say RLC circuits can you model a quantum system with finite Hilbert space. So that's quite a lot. So that's what I do. So I'm right now developing the classical computer emulating quantum computer. That's what. So I do in accordance with my possibilities. So I would say, right now developed in 0.4, let's say, but still our points are under development. So I'm searching for investor. I'm searching for institutions interested in collaboration. That's why I am collaborating with European Quantum Industry. Well, I'm a member of European Quantum Industry Technology Consortium and the Quantum Hardware Systems Company. I can say that I have already 9 fellowships associated with my company, and already 3 Master of Science degrees were defended and were associated with my company as well, and 2 engineering degrees, so like 5 students already certified. So, and then there's like 27 publications already associated with the Quantum Hardware Systems Company as well. So that's the current status. Okay, so very briefly, what we can do in Poland, or let's hope what we hope to do. So let's say I would categorize the Professor Guziewicz work as I would say light level of quantumness by this detectors of superconducting detectors of single photons, because you can have more deeper stages of quantumness. That's why I call it light. So basically, you need to bring the rapid single quantum flux electronics to Poland, and the schemes are already available. Lithography is not so sophisticated. Well, it is sophisticated at some point, but still, it's doable. So you need to bring it to make it operational, to exploit it, to build superconducting processor, because it's hard to even to be competitive in semiconductor processors. That's why I would say, even from the strategic point of view, choice of superconducting processor might be better choice, because you don't have lithography with accuracy of 3 nanometers resolution. This is extremely expensive. So it's very hard to be competitive in silicon. But the superconductor, it's somehow much easier. Then, so you need to prioritize development of massive single photon detector cameras. You have to upgrade the previously finished project of Swish and Professor Guziewicz much more. Then you need to integrate those two guys, and this is also doable. Do we have the professors from Japan and Poland and Germany and so on? Then there is quantum flux parameter next step after rapid single quantum flux, but it's also doable. And then this interface was a scheme, so it could be even Master of Science degree for somebody or PhD, whatever. So this is stage 1, can be accomplished in Warsaw or in Warsaw plus other centers in Poland. That's what I would say. Then let us go deeper. Stage 1A of quantum industrial development in Poland, medium level of quantum, as I call it. Development of rapid single quantum flux coupled with semiconductor quantum dots. So this coupling doesn't have to be fully quantum, but this can be doable, done. And then the adiabatic quantum flux parameter is a bit similar to rapid single quantum flux, also coupled to quantum dots by electrostatic interaction, and so on, so on. So development of rapid single quantum flux coupled with semiconductor quantum dots by inductive interaction. And the same is a scheme. One more time, inductive. So quantum flux parametron coupled with semiconductor quantum dots. Also, this is doable in Warsaw. But I'm not saying it doesn't have to be only Warsaw, obviously. Then stage 2 of quantum industrial development of Poland, at least prospective, in reference to quantum hardware. I call it quantum industry only when does exist hardware. That's my specific definition. I don't fully categorize existence of quantum software as quantum industry from that perspective. There's a realism coming from the chip operation, that the constructor of the solver is omitting certain factors subconsciously at some point or consciously. It has to be always tested against quantum chips. That's what I'm saying. Then okay, so stage 2. So basically, rapid single quantum flux coupled with flux superconducting qubit. Flux superconducting qubit can be done, and that's definitely bought from various companies, and D-Wave, IQM, and so on and so on. There's so many companies you can buy, or you can do under certain industrial group scheme. Then there is a quantum flux parametron coupled with superconducting qubit. This can be done. And then there's development of rapid single quantum flux coupled with transmon superconducting qubit. This is also so many people does transmon qubits that you can do both. Then there is development of adiabatic quantum flux parametron logic coupled with transmon superconducting qubit. So this is somehow the closest to this idea of this hybrid classical quantum mind in superconductor. So this is stage 2. I'm going to finish quite soon. Stage 2A is a deep level of quantumness. I am not saying ultra deep. Development of semiconductor quantum dots based electronics coupled with flux superconducting qubit. So in a sense, criteria is that you have single electron wave packets on the chain of quantum dots, semiconductor quantum dots in quantum regime, and they interact with flux superconducting qubit in quantum regime, and their interaction is in quantum regime. It's a bit challenging. This is what is pursued by MIT right now. That's what I would say. Then there is development of semiconductor quantum dots based electronics coupled with Cooper pair box. That's yeah, quite so first was like D-Wave company approach, D-Wave like. Second was we're coming back to technology from 2004, but this is doable technology. And then there is development of semiconductor quantum dots based electronics coupled with transmon superconducting qubits. So the transmon and semiconductor, well, this could be new kind of standard. So this is stage 2A that can be achieved in Warsaw and other places in Poland as well. Okay, I'm very close to finishing. Stage 2B, achieving deep level of quantumness. And then I would say usage of semiconductor quantum dots coupled with flux superconducting qubit. So you know that semiconductor quantum dots are quite easy and massive. At some point, they will be massive. They already are massive. Then flux superconducting qubit will never fully be massive. It can be sparse, but still, so it can be local quantum chip having low level of noise, interface with quantum dot chip, semiconductor quantum dot chip of higher level noise, and then this can be even this and interface to another semi-classical superconducting chip. So in a sense, you have here hybrid semiconductor superconducting quantum computer interface to classical computer. So this is this type of architecture. Then there is development of semiconductor quantum dots based electronics coupled with Cooper pair box and coupled with adiabatic. So the same version as before, but right now we replaced flux superconducting qubit with Cooper pair box. That's how it is. Then we have development of semiconductor quantum dots based electronics coupled with transmon superconducting qubit. So in a sense, this is the best already existing superconducting technology, transmon. Also quite spread. So we have quantum dots coupled to transmon, and then this transmon is coupled to classical classical superconducting computer. So this is hybrid classical quantum superconducting computer coupled to another semiconductor quantum computer. So this is stage 2B. Of course, and there are a bunch of references. I have not. I just touched some of them, like Professor Guziewicz's work was already described. The link was before. So you can trace of them, yeah, in greater detail, and that's it. So I welcome your possible questions and comments, and I'm sorry that it took so long time. I guess it was quite lengthy.
No problem, no worries. That was quite interesting, so thank you, Krzysztof. Okay, so do we have any questions? Maybe I can ask first. So, yeah, because as you know, we are at the beginning of working on this, let's say, Polish quantum national strategy. So, what would be your, let's say, the biggest recommendations for the public sector, if you could recommend, because you've mentioned some points already, but maybe just to summarize, let's say, three most important points.
Okay, so let's say I will share my my kind of recommendation based on my previous experience of being employed at two different universities. So I would say you cannot treat the specialization in quantum technology is the real specialization. I don't even consider myself to have fully real in the sense that I'm still trying to be more experimental in that sense. I'm not real because I'm just theoretician. But I would say you have to award institutions for employing people doing explicitly quantum technology.
Mm-hmm.
So let's say you want to work at University of Warsaw on quantum technology. You cannot have more than 20% of didactics that takes your time. And you need to be given special money just to develop quantum technology. And you need to be evaluated for technological outcome more than just for then publication outcome. So you have to make internal scheme of management that is not the same as scientific, that is more of technological nature. It's very critical. So I would say, so you have to make a state inside the state in a way. So, and then if you give certain money for employment people for this devoted purpose, and they only work on this devoted purpose, and they are not forced to just publish for publishing, but they are forced to at first to do quantum hardware and secondly publish, then you can change the political climate And this is absolutely necessary. Like I had a conversation with Professor Hannes Töpfer from Germany, that is expert on rapid signal quantum flux electronics, and he says to me that even Germany has this always this they only grant new ideas, but let's say you have to accommodate this proficiency of creating qubits. This is not purely new knowledge, but this is a lot of knowledge and skill. So if you want to create a team that can acquire such knowledge, they cannot only be judged on the level of novelty. I mean, you have to be more, you have prioritized technology more than science if you want to do quantum technology, really. I mean, because what people are confusing, they confuse quantum information science with quantum technology. And this is very, very often confusion. But we're absolutely experts on quantum information science. But unfortunately, somehow they are not biased or they don't have much ambition towards being so much proficient in quantum technology. So this is very necessary climate that needs to be changed. And second thing, I would say lithography, access to lithography for this devoted targets. This is very essential to especially to have a low level of bureaucracy for accessing lithography. This is very essential. So those two things are really necessary. And since we have very dropping level of students in physics, let's say, then we should start those programs quite immediately, because we have less and less potential requiring getting new people, and the world is even more and more competitive. So we're supposed not to wait. So I'm not sure if I was so much you know informative in my answer. And the last thing is put certain prioritize on certain technologies. There's more than 20 existing technologies. You cannot pursue all of them. You have to choose. So you have to break the symmetry of, I would say, how do you call it? You have to be not democratic at some point in the choices, because democracy and infinite ideas, infinite pluralism, I would say. You have to deny existence of infinite pluralism in ideas. You have to choose certain directions that are prominent from industrial perspective. So that's very essential. And like just have a comparison of Ireland and Poland. And Ireland is quite small country, but I have certain access to I have certain knowledge of what they do, and they're much more before us in doing this, because they treat this quantum industry seriously. And when you build industry, you try to hit new things. So don't think only by fashion, think by potential. And definitely, Institute of Microelectronics and Photonics supposed to have really big budget for that. I believe at Cesamat as well, and also a couple other places. So without budget, I would not say that politicians are thinking seriously. I'm sorry for such long answer.
Okay, that's fine. So it's actually very good points, and especially regarding this prioritization. So, in your opinion, because you know a lot about different quantum technologies, so on which technologies we should prioritize, let's say?
Semiconductor quantum dots. I think that definitely people should supposed to do it massively in Warsaw right now, because they're already expert in semiconductors. That's for sure.
Okay.
Well, uh, it's a little bit difficult answering for me because things are biased politically. And Josephson junctions supposed to be prioritized, and like I don't know, you're supposed to increase certain people budget 10 times, 20 times to those people that are already experienced Josephson junctions. And Josephson junctions are the must, because in a sense, let's say coherence time in semiconductor quantum does it like 10 nanoseconds, not long. In Josephson junctions, you have 100 you have 100 microseconds, even more. So Josephson junctions must be reactivated very seriously, even more than just fundamental research. But this is really troublesome, because like there's, let's say, Polish NCEN is prioritizing Hirsch index and publications, and those people are behind this decision. So perhaps new agency needs to be somehow uh, let's say, founded. And I would say I will be provocative. I'm more physicist than electrical engineer, but from quantum technologies, perhaps you need more electrical engineers than physicists. Physicists are necessary, but believe me, the world is changed of technology is mostly changed not by physicists, but by electrical engineer that takes physicist ideas into real action.
Mhm.
And this
Okay.
is the way of thinking not really much present in Poland.
Okay, that's a good point. Thanks for this. Okay. Do we have more questions to our speaker?
Professor Marek Guździewicz is with us, or is it?
Yes, he just thank you for interesting presentation. So he is with us.
It was quite lengthy.
Yeah, that's fine. Maybe professor would like to give a comment or
I mean, imagine you want to be Elon Musk. You want to beat somebody. You just imagine
mm-hmm.
from that you're a competitor. You want to win. You
Yeah.
cannot. You have to. Let's say you want to be the best in given architecture. You have to really prioritize the organization structure, the financial link, and so on and so on. I mean, think from that perspective as a battle, not as a just
Mhm.
collaborate, as a technological battle. Then you have to choose the priority and targets and be very consequent in action. That's what
Mhm.
I can say.
Okay, that's good. All right, I do not see more questions now. So, Krzysztof, thank you once again. And I will just show some slides for the end and announce your next lecture next week. Uh, so, yeah, there will be the next Warsaw Quantum Computing Group meetup next Thursday. So let me share my slides again. Okay, hope you can see them. And yeah, so we thank everyone for the for attending this event. So we hope that you enjoy it. I will later send you a feedback form, and we are always keen to listen to your feedback and improve our events. If you would like to stay in touch and hear about the next events, you can join our mailing list, our social media groups, or follow our YouTube channel. We'll try to upload the recording to our YouTube channel later. You can also subscribe to our monthly newsletter or join our QPoland Discord server to have discussions with our community. And in our newsletter, we also publish the news from the quantum world that we collect over a month usually. So once again, we thank our strategic partners and our honorary partners as well. If you would like, you can also donate us. You can also donate a percent, 1.5% of your tax if you are in Poland and you pay taxes in Poland for our statutory activities. And finally, would like to invite you to our next meetup. As I said, next week, next Thursday, Krzysztof will give another talk. This time, the title is Electrostatically Interacting Linear Qubits in Curved Space. I'm not sure if I spelled correctly. So, Krzysztof,
Yes,
maybe you can
it's
maybe
correct. I
yeah,
promise to be
maybe
more mathematical this time because today I was
okay.
very much chip oriented. No, it was no equations almost today.
That's fine. Maybe you can just give a brief introduction already, just to tease people and encourage
All
them to
right.
join.
So the talk will be on the modern approach to CMOS-based quantum computation using single electron devices. And so I will describe theoretical scheme with intention to design new experiments. So it will be about, and I will also have an ability to model even some general relativity structures in these nanostructures. I will try to be both fundamental from technological point of view and quantum computation point of view, and also have some reference to other fields of physics.
Mhm. Okay, sounds great. So we are looking forward to it, and we'll start the registration later today. So thanks everyone for joining. Hope you enjoyed, and we hope to see you next time. I will now stop recording and stop sharing my slides.
There is Jacek. Is there Jacek? You want